Can everybody hear me okay?
Nope, let's get that microphone down a little.
Okay, how about now? Okay, good. Good morning. Welcome to solar power, which we won't have much of for today. But I went down and looked, and we're actually at 1% right now with the fog and the mist and the rain. So we're getting about 3 kilowatts of power out of this shady day. So we're going to talk about solar power today. So here's what we have. This is the solar power. The sun is up there. It's shining on the atmosphere. Some of it will be reflected back by the atmosphere at the very top. Some of it will come down into the atmosphere and be reflected, re-radiated as IR. Some of it will come to the surface and be re-radiated, but most of it will be absorbed on the surface of the Earth. The surface of the Earth will then re-radiate on the right-hand side. You can see the arrows going back out into space. We're going to be losing some power as we go along. So I'll talk about these guys in a little while and show you a short movie, but these guys were putting on the solar panels up on the roof a couple of years ago. And this guy is saying, maybe I should be giving out solar panels instead of coal to the naughty little kids. So this is a roadway in South Korea. The center of the road is covered with solar panels, and it's a bike path. So they are able to ride their bikes, not in the sunshine, and they're generating electricity from the roadway. So it's not interfering with anybody's yard or whatever they're looking out their window to see. This is a solar tree in Africa. It looks kind of like a palm tree or whatever, sort of like an African tree, but what it really is a bunch of solar panels. And you can see some people sitting down that are using it to charge their phones or their computers or whatever. So what we're going to do today, we'll have a thought experiment, which will have to be totally a thought experiment because we can't actually perform it. And thought experiments were a favorite of Albert Einstein because you could sit at your desk and you could think through the whole thing without having pencil and paper or anything else. We're going to have the Oak Hammock solar panel movie. Our sun is an ordinary sort of a star. I'll be talking about the sun and how ordinary it is and how special we are not. Solar energy, historic applications, solar energy conversion history, solar energy storage, which is very difficult, but we'll talk about it. The future of solar energy, pros and cons of solar energy. So here's our thought experiment. We're going to send an observer out into the Duckworth Gardens to look up at the sun and tell us exactly what the sun is doing right now. Of course, it's a thought experiment because we're fogged in. The task will be to report back on what the sun is doing right now, and we'll talk about it. Actually, you can't go out and look at the sun, even if it is shining, and tell me what it's doing exactly right now, because it takes 8 1/3 minutes for the sunlight from the sun to get here. So we never know what the sun is doing. We know what it has done recently and what it has done more in the past. So this is, and now we'll have to figure out how to start the movie. Here comes the movie starter. So this is a short movie about the installation of the solar panels here at Oak Hammock in late 2021, wasn't it? October of 2021. I'll show you that in a minute. Ready. These are the solar panels. You can see how tall they are next to some people. So they're a little over 6 feet and they're about 2 feet wide, more or less. And these are the people that got this thing going, signing the first panel that'll go up on the roof. And I'll tell you who they are, and you'll recognize some of them. And there's their signature. So it's a two-man job because of its length. And it probably weighs of the order of what, 80 pounds, Paul? 70 or 80. And here's the way you get them up there. And those of you who lived in building 1 or building 2, when they were doing this, you could watch these guys. I am glad I didn't have to install them, and so are all the rest of the people here at Oak Hammock, because they're up on the roof that's almost 5 stories high from the ground. And they're running around. You can see they have ropes on them, but I don't think the rope does much because he's just lying it down on the floor. I guess it will catch him if he goes over the edge. But these panels are held on to the receivers that were put there in advance after they put the new roof on. It was one of the things that we were waiting on, besides approval of the board of directors to enter into a contract. So they're held in by how many bolts, John? Do you know? A few bolts. And they've withstood a little bit of wind. 45. So they're still up there, and these are the guys that put them up. And there'll be some drone shots of them flying around. So that's really about all we need to see on that one. Solar Impact was the company that did it. Okay. In 2017, a group of people, Nelson Logan, John Paul, Bill Zagel, and others, formed a feasibility committee to see if it would be possible and feasible to install solar on the roof of Oak Hammock. In 2018, they prepared a presentation to the board of directors of Oak Hammock, and they got an RFI on the street, a request for invoice information to 2 of the local solar panel engineers. Both submitted proposals. In 2019, on July the 17th, contractors submitted best price proposals. In October, Bill Rossi, who you saw signing it, you saw John Paul signing it, Bill Rossi and a team went to the board of directors and presented their findings, and the finance committee of the board of directors approved it, and then the board of directors approved it, and Solar Impact was selected based on their request RFP that they answered. July, they started installation in building 2, in October in building 1. So there are 2 solar installations, 1 in each of buildings 1 and 2. The total cost was around $600,000. The estimated lifetime is 20 years with a probable lifetime of 30 years, maybe even longer. So the installation dates you can see there, and the peak power, building 1 has 242 kilowatts, and building 1 has 164, so a total of just over 300 kilowatts on our roof. And so I told you we were running at 1%. I ran down to look at it out of curiosity, and the meter said 1%. So we're getting 3 kilowatts out of the fog and the glare. So the total power to date is 319,000 kilowatt hours. And out of building 1 and building 2 is, because it has a bigger panels, if 454, total of 773 kilowatt hours. Total savings to date, because the projection was made based on a kilowatt hour charge by GRU of around 9 cents per kilowatt per 1,000 kilowatt hours. 9 per. About 12.
11.7.
Yeah, so 11.7, and now they're up to around 13 or so. And then when they increase the price, we get more savings because we're getting the 300 kilowatts hours out of the solar panels up on the roof. So it was a good investment. It was projected to pay off in something like 11 years. And now it looks like it'll pay off in somewhere around 6.5 or 7.5 years. It's about $2 per watt with a little smiley face. Okay, where are stars coming from? Stars come from the solar nebulas that are out all over the universe. This is from the James Webb Telescope, and this is a collection of dust and atoms and space junk. But when it gets together close enough, gravity will take over and it will coalesce and it will start to form a star. Gravity will then make the star more and more dense, and it'll begin to heat up the interior of the star, and it will flare off and start with fusion, changing the hydrogen, which is the most prevalent atom in the universe, into helium. And we'll see about that in a minute. I thought this was an interesting one. It's called the Running Chicken Nebula. And if you look at it a little bit, the head is up on the right, the feet are kind of straight down from the head, and the body of the chicken is there on the left. So anyway, here is our sun. It's really an ordinary sort of a star. Here's a comparison of our sun with some other stars that we have heard about. The sun is there on the left with the arrow. There's lots of other stars that are smaller than our sun, and there's a number of them that are way bigger. Betelgeuse is in red, Rigel is in light blue, Sirius is inside of Rigel, bigger than our sun, looks like about a factor 3 or 4, Aldebaran and Pollux. So we really are an ordinary sort of a star. How do the stars form? Well, they have the nebular clouds with all the dust and the hydrogen and a few other elements that then coalesce, and the gravity takes over, and the star will then start creating light and heat. And later on in life, it'll change from burning hydrogen to make helium and other elements, and it'll be more taking the helium to make bigger elements up to and including iron. And then at the end of life, it becomes a giant red star, and then it creates its own nebular cloud, and it goes away to either a small white dwarf or just burns out. So here's where we are in our own life cycle of the sun, about 4.5 billion years ago. And it's really funny to talk about years because time is a concept invented by humans. The year is one circle around the sun by the earth, so it means nothing to anybody else, but it's how we can think of time and keep it. So we're about 4.5, 4.6 billion years into the life of our sun. It will grow and get hotter as it goes along. It'll become a red giant, and then a nebula, and then it will kind of burn out and become a white dwarf. That's the normal status for a star like our sun, a very ordinary sort of star. This is just showing the two different kinds of, or two of the kinds of stars in their life cycle. You have the stellar nebula, you get a average star in the upper line or a massive star in the lower line. And the upper star turns into a red giant toward the end of its life, and a planetary nebula, and then a white dwarf. The red supergiants will turn into a supernova, and that's a huge explosion that lights up the universe, and that's where most of the other elements are created when that is going on. And then it has two ways to go, or maybe more. One is to become a neutron star, and the other is to become a black hole. So the sun will be its most active in 2 decades. I found this in the Post the other day. Here is the solar minimum, which we had been running on. And on the right, you see the black dots and the solar maximum. The black dots are sunspots, and they are aberrations in the surface of the sun, and they will cause a lot of radiation to be thrown off, a lot of elements, high energy nuclear particles. And you get this. This is the northern lights. How many of you ever seen the northern lights? Yeah, I saw them when I was in Ithaca in graduate school there. And Carol and I saw them when we went to Alaska in late August because it would be warm in Alaska. We decided to go camping. We saw the solar lights. We froze our buns off because it was still below freezing in late August in Alaska. I have not seen the solar lights that colorful. Okay. Here are close-ups of the sunspot and solar flares over on the right, but the sunspots are cooler. Now, cooler in terms of the sun's temperature are still hundreds of thousands of degrees, and it doesn't matter whether you're using Fahrenheit or Kelvin at that time because it's really, really hot. So this is just a little thing to show. Another part of the paper showed up yesterday or the day before. The moon is receding at 3 centimeters per year, and one day it will no longer cover enough of the sky for us to have a complete solar eclipse. How can you tell how big is a centimeter? A standard paper clip is about 1 centimeter wide. The wires in a standard paper clip are about 1 millimeter, close enough to allow you to visualize the distances. So the sun is not, the moon is not moving rapidly away, but some year in the distant future, no more total eclipses. Okay, how old is the sun? At least 4.5 billion years. How far is it? About 150 million kilometers away, 93 or so million miles. The time for sunlight to reach us is 8.33 minutes, which you can easily calculate if you want to, because we know how fast light travels and we know how far it is, and then it works out. A back of the envelope calculation will give you something around 7 or 8 minutes, just rounding everything up to divide by 10. The diameter, 1.4 times 10 to the 6 kilometers, 109 times the size of the Earth. The volume is 1.3 million times the size of the Earth. The mass is 333,000 times the mass of the Earth. And the magnetic field strength on the surface or near the sun is something like 3,000 Gauss. The Gauss is about 1 times what the polar magnetism is on the Earth. So this shows about 0.7 Gauss at our North Pole. The density in the center of the sun is 160 grams per cubic meter. Water is 1, and gold is about 19. So it's very, very dense in the center of the sun. The temperature of the interior is 15 million degrees Kelvin. On the surface, around 5.5, near 6 million Kelvin. The temperature on the corona, which is the crown around the edge of the sun, is 800,000 to 3 million Kelvin. Radiation of the entire sun, 3.6 times 10 to the 23rd kilowatts. That's a bunch. By the time it gets here, it's about, or on the surface, it's 6 times 10 to the 4th kilowatts per square centimeter. The solar radiation at the Earth is about 0.136 watts per square centimeter. The brightness versus the full moon is almost 400,000 times as bright. I haven't gone to look. John, have you gone to look at the full moon on your indicator and see if you're getting anything out of the solar panels?
Inverters aren't that good. It's 0.
Yeah. Okay. Sun's composition by weight. I told you hydrogen is the most prominent element in the entire universe. 73% in the sun. Helium, because that's what it's making out of the hydrogen. We'll talk about that in the last lecture. We'll talk about fusion, converting hydrogen into helium. There's some oxygen there, less than 1%, carbon, a couple tenths of 1%, iron. Iron is the heaviest of the metals and elements that the sun can create from its fusion. The heavier elements are created in the supernova that comes from the super red giants. There's a little bit of nitrogen, less silicon, less magnesium, and less sulfur. So historical uses, what have we used the solar energy from the sun on Earth? 1500, the Egyptians had sundials. That's probably not a 1500 BC Egyptian sundial, but it is a sundial. And there's always a funny meme on Facebook every time we change from standard time to daylight savings time. You have to go out and rotate your sundial a little bit, and you have to go to Stonehenge and move all the stones. For centuries, man has dried fish in the sun, and we've seen some of those when we've been on cruises like to Norway and other places where they do a lot of cod fishing and drying. They didn't have the PVC pipes that they're being used now, but these are racks of fish drying in the sun. Sea salt from solar panels, it's been done for millions of, or thousands of years. Get some seawater in a pond and let it evaporate long enough and you can get the sea salt. This is in Bonaire. When we were in Bonaire many years ago, we saw some of the salt flats that were tended by the slaves, and we saw the little slave huts where the slaves lived to work on the salt flats. Sea salt is taken from the pins, and I always wondered, how pure is that sea salt? Because it's sitting out there, the birds fly by, there's all kinds of things in the atmosphere, in your sea salt. So we don't use a lot of it at our house. Clotheslines. My dad made a clothesline very similar to this. He welded some 4-inch steel pipes into T's, stuck them in the ground, and ran lines back and forth, and that's where Mother dried our clothes. That was when we didn't have a dryer in the old days. A solar survival mirror. This is interesting. They're in life raft kits on ships. And I got an old life raft kit that was surveyed out of the Navy, and I had a solar panel emergency mirror at one time. You look through the hole in the back, and the mirror will reflect a ray just like it shines off your windshield and blinds you sometimes when you're driving in traffic. But you try to then flash that light. If you see an airplane, you want to flash the light by the airplane, and you can watch the solar, you can kind of see where it goes, and you can aim it at the airplane to wake up the pilot and tell you that you're down there. There also is solar survivor stills. I had one of those. I never tried it out, but you put it in the fill it, or not fill it, but you put in a quantity of seawater in it, and there's a clear plastic dome which heats up the seawater, but the dome is cooler than the steam from the seawater, and it collects on the plastic and rolls down the side into the collector, and there's a little tank you can get. I never tried mine out, and I have no idea where it is anymore. Here's another use at Oak Hammock of solar power. I frequently will put my coffee mug in the sun to keep it warm so I can drink hot coffee all day long. Historic uses. 7th century BC, lenses were used to light fires. It doesn't say where they got the lenses from. I suppose it was they picked up some old shards of melted volcanic glass, and they found out that you can light a fire. Most of us have done that. How many of you have set paper on fire with a lens in your backyard? A few of us. We didn't tell our mothers what we were doing. 2nd century, Archimedes used a bronze shield to set warships on fire. Right. I think I need to talk to Nancy Dixon about this to find out if it's a myth or if there's any truth to it. I believe it's more a myth. At 20 AD, the Chinese were using burning mirrors to light torches. '100 to 300 AD, the Roman bathhouses that you can still see in various places in Europe, they had a south-facing windows to collect some heat from the sun, for their bathhouse. The sunrooms on the Roman houses were also used at that time. And the Justinian Code is similar to the New York City Code. You're not allowed to build a building that'll block somebody else's sunlight all day long, so they can still have their solar heated room. Mesa Verde in 1200, south-facing cliff dwellings. And my first roommate at Cornell was a national park ranger at Mesa Verde when he came to Cornell. He didn't like it back east, and he left and gave me all of his neckties because he was going back to the Park Service where he didn't have to wear a necktie and he could be himself again. And he gave me a little pheasant, a flying pheasant tie tack of 7 colors of gold from the Black Hills of South Dakota. Hot boxes for cooling. I found this on the internet, but one of my professors at Cornell had been involved with the United Nations project to create solar furnaces like this for use in Africa for people who couldn't have wood to make a fire so that they could cook their food. And she said it worked very well. She'd never brought one in for us to see. The Stirling engine. Now, this is a crazy device, and I'll show you how crazy it is later. But this is a little model of a Stirling engine. It is an external combustion engine. That is, the fire is outside the engine. There used to be Stirling engines in the old Mazdas in the 60s or so, I think it was. I'm not too sure. They don't do that anymore, but this is one, and we'll see one kind of a working model later. Becquerel discovered the photovoltaic effect, and this was it, an acid bath, platinum electrodes with sunlight coming in or light coming in, and it would generate electricity from the platinum plates, like a lead acid battery that we have in our cars. Very similar. This is a gentleman in the Paris Exposition of 1860 something or other. He had a solar powered steam engine that he was demonstrating in the streets of Paris. So he has a solar collector that's reflecting the sun's energy out into at the end of the tip of that black part in the middle of it, to convert the energy to heat up the steam and power the little steam engine in the lower left. Still an idea in use. Willoughby Smith, selenium photoconductivity, and then with his cohort Adams later, they did selenium photovoltaic effect. So in 1876 was the first time that people knew that you could have sunlight power a little thing and make some electricity. Not very much, but it worked. And this is how it worked. You had some vitreous selenium in the center, and you had some connectors on either end with platinum wires and a glass tube, and it's about 1 to 2.5 centimeters long. 2.5 centimeters is an inch. So it's not a very big device, but it was a test. And since it's in a tube, it must have been a test tube. Charles Fitts, first selenium wafer solar cell, whopping 1% efficient. But that was in 1883. And so a very thin layer of gold with a little much thinner layer of selenium and a brass on the bottom, and you could get electricity from that. Later, first commercial rooftop solar hot water heater. When I was a kid here in Gainesville, we had friends that lived out on the Archer Road past what's now I-75, and they had a large old Florida-style 2-story, maybe 2.5-story house. And on the top, they had a solar collector that made the hot water for their use in the bathtub and possibly in the kitchen. I'm not sure about that. Einstein published a paper in 1905 about the photoelectric effect. And then that's the only thing for which he received the Nobel Prize 15 years later. The photoelectric effect says that if you have an electrode and the sun hits it, you will only get off electrons emitted by the energy of the ray of light that hits the electrode, and it only comes off at a certain energy, and that energy corresponds to the energy levels of the atoms which are being excited by the solar or light source that hits the electrode. In the inverse of that, you have neon lights. 54, Bell Labs came up with a PV, photovoltaic cell, that was around 11% efficient. What's the efficiency of ours, John?
In and around somewhere around 29%.
So it's an increasing, an amazing improvement in capability. Vanguard 1, the little satellite that the Navy finally put in orbit after blowing up a few rockets, had a 1-watt solar panel on it, and that powered it for its lifetime. And I think all it did was run around the Earth and go beep, beep, beep. Ooh, I hit the wrong one there. Let's see where we are. That was the shut it down thing. Okay, now we're back where we were. In the 70s, Exxon had a cost reduction from $100 per watt down to about $20 per watt. That's a very large increase in the efficiency, but nowhere near what we have now. Like I said earlier, ours were about $2 per watt installed. So these are the Exxon boys and girls with their new $20 per watt solar panels. University of Delaware had a solar house. It was photovoltaic as well as hybrid, and sells their excess energy to the grid. And this was a picture of the University of Delaware's solar house in the early 70s. In 77, the US created the Solar Research Institute, and it's now the National Renewable Energy Lab for geothermal, which we'll talk about probably the last day, solar today, wind next week, waste energy, either the 5th or 6th talk. We'll get into waste energy, but that's all under the NREL. First solar powered airplane. I don't think I want to fly in it. '82, the first megawatt PV photovoltaic generator, and you can see how big it is. And that was probably in the 10 to 15% efficiency. So now you could probably get a megawatt out of maybe half that size. '82, first solar powered car in Australia. Again, it wasn't really going to be a great improvement or anything, but it was a concept just to show that it could be done, and it went several thousand miles. University of South Florida developed a thin film photovoltaic cell at 13% efficiency. And this is just a picture of it, but it's multi-layered. You have a layer which is receptive to electrons. You have another layer which will give off electrons with the solar power, and you hook it up and you get your electricity if you stack them all over the roof like we have here. This is now a different thing. These are solar collectors, like that guy in 1860 in Paris. He was collecting the energy from the sun, concentrating it on a device to make the steam to run his little steam engine. So there's several ways of doing it. In the upper left corner, you see a trough of reflectors, and you put the pipe running with some oil through at the focus of the thing so that you can collect the concentrated energy. And we'll talk about that in a little bit. Lower left, you have a concentrator separate from the mirrors, and you have heliostats that are moving around to direct the sun's rays onto the concentrator. In the upper right, you have something similar, but they're vertical mirrors with a vertical concentrator. And in the lower right, this is what the guy was using in 1860s. It's an elliptical or parabolic reflector reflecting the rays out to the concentration point, and then they'll do something with it, and we'll see some of that in a minute. This is a solar concentrator, and you can see the PCU up in the upper left is the power conversion unit. And it could be a Stirling engine, or it could be something else to make steam. And you have the receiver, which is receiving the reflected rays from the parabolic mirror. And if you look carefully, let me see if I can, oh, my left foot's going to sleep on me here. There we go. So look down here. This is a track with wheels. So it has to be able to rotate around in the horizontal plane. This is a suspension device on the support so that you can rotate it up and down, because the sun will not stay in the one place that you'd like it to be for your concentrator. So this has moving parts. It has some kind of a collector, and you have to do something with the collected energy separate from the concentrator itself. So solar energy conversion, what can we do with the solar energy? The AC generator can be used from the solar concentrators to run a steam turbine. And this is a description of it. In the left side, you see the field of mirrors with the oil pipes running through them to collect the energy from the sun, and it can be sent to two different places. On the far right, you can see a steam generator and a steam turbine with the condenser, and you pump the water back and forth like any steam generator that we'll talk about over and over again. On the middle left, you see the steam generator is using the hot oil to create the steam. But there's also some storage devices in the middle. You can change the plumbing around. So if you don't need the steam generator generating electricity, you can store some in salts, and then later you can run the pump to take the energy out of the salt through the steam generator and run the turbine again. A whole bunch of moving parts. AC generation in the solar concentrators, the Stirling engine. Now here's this Stirling engine. It's a bizarre thing. You can see that the heat is on the outside, and the blue is cooler air, and they're going to get heated up and turn into pink air. And there's two pistons running back and forth. The piston on the far right is pumping the air back and forth, and the big piston on the left is getting the energy out, and that's what's turning the big wheel. And the other device running that little piston takes the hot air into the fins and the radiators to cool the air. The air stays in the Stirling engine, and it just gets hot and cold and hot and cold, and it's bizarre. DC generation, photovoltaic generators only make direct current. And for AC, there's no AC battery, but for DC, you can have a DC battery. This is a diagram showing very similar to what we have here. On the left, you see the grid at the top. In this case, it's allowing electricity to come into the meter and fuse box, or electricity to go back out if you have a battery. We do not send any of our electricity back to GRU. We keep it in-house and use it to reduce our electric bill. So we don't have the battery that's shown there as optional battery. This is a ridiculous thing. And all it's trying to show you is up in the top, you can have an AC converter. We have an inverter here for Oak Hammock. The DC goes to two different inverters.
Each building has its own inverter.
And so those turn the DC into AC and put it into the building. The one on the top is using, if I can read it, I'll tell you what it says. It's using a bidirectional inverter, DC to AC or AC to DC. We don't have that. The one in the bottom shows a photovoltaic inverter, which is what we have, and it only goes to our building. Okay. Solar energy storage. Thermal storage, I showed you that one case where the converter or concentrator was running the oil into a bath of salt to try to save some of the energy for use later. Hydrogen manufacturing, you can use the DC that you get from the solar panels to create hydrogen and oxygen from electrolysis, a very inefficient way. There are other ways that are somewhat more efficient, but it's not generally used with photovoltaic inverters. Battery storage, we'll talk about batteries in a minute, but you need a really big battery if you're going to try to store some energy and put it back through your inverter to get electricity for use in the house. You can have a lead acid battery. These are lead acid batteries. I could not find a picture of the submarine batteries. Each one of those cells is about 5 feet tall and 1.5 feet by 1.5 feet. The submarine batteries are bigger. They're a lead acid battery, and we had 125 or so in each of the battery wells. In the diesel submarines, they had 2 battery wells, and you could take the 125 battery cells would make about 220, 250 volts. You could put those in series to run the electric motors that would propel the submarine. But we had a thing called the half-hour rate. If you really wanted to go through the water rapidly, you're going to deplete your batteries in a hurry. So the diesel boats always had to snorkel to recharge the battery with their diesels or come to the surface in World War II to charge their batteries. So in the submarines, we had to dive the battery wells. You had to take off your rings and your watches and anything else metallic and go down there. We had the electrician's mate that were in charge of taking the specific gravity and checking if everything was okay. If we needed to add pure water to the battery cells, they did that. And we would have to do a thing called an equalizer charge on the submarine ever so often. After you do some quick charges, the battery gets kind of used to that. So you run it for about 18 hours on a slowly decreasing charge so that you can kind of equalize all the cells in the batteries and bring them up to their top efficiency. So those are lead acid batteries. You can have lithium ion batteries, and we have those in our watches and our cell phones and all over the place. And this is showing how in the lithium ion batteries, the electrons aren't flowing, it's the ions of lithium that flow back and forth. So if you're discharging the battery, they flow in a fashion so as to give you electricity. If you're charging it, you push them back to where you put them in a higher energy area so they're ready to give you some more electricity. Our cell phone batteries typically last for 48 hours or so. Mine is usually showing about 60 to 70% charge when I charge it each night. My watch will tell me, let me see what we have there now. Wake up, watch. I'm at about 86% now because I charged it last night before I went to bed. The air iron batteries, this isn't a concept that they're trying to work through and get it to work because iron is cheaper than lithium. And if it works and they're still working in the lab with it, this guy is working on the iron battery. It's kind of like the lead acid battery, except you have iron instead of lead and air instead of sulfuric acid. Then there was the hemp battery. I think a bunch of guys were sitting around smoking pot and they said, hey, wouldn't it be cool if we could use this for electricity? There are some companies that are working on developing it. Pumped hydroelectric storage. And we'll get into that. I'll show you in the United States, we have the largest pumped hydroelectric storage capacity in the mountains of West Virginia and northwestern Virginia. I'll show you that later. But this is the concept. During the daytime, you have your solar collectors on the left. They are generating electricity through an inverter and it goes to the city on the right. And if it has excess electricity, it goes down to the lower part of the reservoir and the turbines are run backwards and they pump water up the hill to the upper reservoir. And then at nighttime, it reverses. The solar panels aren't doing anything. The water flows from the upper reservoir down through the turbines to the lower reservoir and generates electricity, which is then sent to the city. So that's hydroelectric storage. This is a graph which is confusing as you look at it, but there's a horizontal line near the top where it says 1500. That shows that your capacity for generating electricity is 1500 kilowatts. The red line shows what you actually need at the time of day. And then nighttime, you don't need as much energy. And the daytime, you need more energy because people turn everything on. And again, in the far right, in the nighttime, you don't need as much energy. So if you're generating the 1500, you only need 1000 on the left-hand side. You can put it into storage. And so all of the power generated that you don't need until about 9 o'clock, you can put into storage. And then when you need to, you can recover from storage to cover the excess of energy requirement on the red line above the horizontal green line. So numbers aren't important, it's just the idea here. So this is solar expansion plans. And the lower chart is showing the number of solar panels that are being created. The red chart at the top is the total number of solar panels that are in service. And in order to get solar panel to the level that they want by the 2060, it looks like we're on track. The projected lines indicate that we're on track to get there. Maybe. These are just showing what is the cost of your electricity. The top line is showing that the photovoltaic cells power generation is really down low. It's about the cheapest power you can get if the sun is shining. The bottom one show solar voltaic. Let me find. Hello. So the bottom picture, where is there it is. The bottom picture, the red is showing solar photovoltaic price against time in dollars per kilowatt. The grayish area is the fossil fuel power range of cost of producing electricity from 5 to 18 cents per kilowatt hour. And The blue is offshore, dark blue is offshore wind. It's far more expensive than onshore wind. So we'll look at a bunch of these things just for comparison. These, if you look where the blue arrows are, the solar thermal concentrated is about 5 to 6 times as costly as solar photovoltaic. Solar photovoltaic with storage is about 50% more expensive because you've got the battery and all of those things. The rest are just all kinds of other things. And they show you what is the cost per kilowatt hour. And they vary at the top for coal power and through nuclear, natural gas, down. We don't need to look at all of that stuff because I'm going to bore you with it on another. How did I do that again? I'll bore you with another one later. So this is showing you on the left, the fossil power. Coal is more expensive than gas. Gas is more efficient than coal. It's cleaner. It has about 60% less pollutants into the atmosphere, CO2 and methane. Gas peaking we'll talk about when we get into the others, but in Crystal River, they built 2 gas turbine combined cycle units, and those can be run up and down in energy fairly easily to provide energy when you need it. And if we get to all renewable wind, solar, and other renewable energies, you're still going to need some kind of constant power level because the sun doesn't always shine, the wind doesn't always blow, and the train with the coal in it may fail to make the target. So the renewables, you can see how the solar panels at a utility scale have come down hugely in price. The solar towers with the concentrators are still more expensive. They're not really quite competitive. And again, they depend on having sunshine. And the onshore wind is decreased in cost quite a bit. On the right-hand side, you can see geothermal, and then the nuclear is going up, the cost is going up. And actually, there have been a number of nuclear power plants that were on the drawing boards and were approved and were canceled because they haven't been cost effective. Okay, comparative cost. Again, if you look, the size of the units is increasing. And as we get higher capacity, the price is coming down dramatically for solar and for onshore wind. Offshore wind is coming down, coal is about constant, and nuclear prices are going up for providing us with the energy that we need. And this is just another one showing different kinds of power and how, as we go along, the price is changing and reducing for nearly everything except nuclear. And another comparison there. Too many comparisons. This one is interesting but very confusing. But a thing to notice, the second bar here is showing a 300 kilowatt with battery, but the storage capacity is only 4 hours. So you're going to get sunshine. Our peak use here, our peak power through our photocells is probably from around 10 o'clock to 2 or 3 o'clock when the sun is at the highest, and it's at the right angle. So this guy can give you some power, but when the sun quits shining, you have only got 4 hours to use it. So this is 500 kilowatts and its price. And you can see that all those other colors we're not going to talk about. They are talking about the various things that go into the cost. administrative costs, the design work, the site selection, site preparation, and all that stuff. And we don't care. Okay, this is the site availability comparison. And the site availability, you can see, goes up and down. Part of it goes up and down because the sun is not shining, or there's not enough water flowing through the dam, or the geothermal steam. I don't understand why geothermal is that low. Once you got it up and running, it would seem to me you're going to be at a higher percentage. The nuclear power, I added it to the chart because they left it off. Nuclear power is designed to be turned on and run for a long, long time at full power. It's a major source of continual energy through the grid. And coal power is up in that sort of a range. But biomass depends on how much wood you have to dump into the furnace. The waste energy depends on how much garbage you have, and I'll show you pictures of those in one of the other talks. But this is just showing you that it's up and down. Solar is much higher in the summer, of course. Sun shines more, it's hotter. Okay, future uses of solar energy. There are no solar panels made in the USA currently. There, one of the recent bills that went through Congress, there's a bunch of money for manufacturing photovoltaic cells. And I think in the Northeast somewhere is where they're trying to put in a factory. The decreasing cost of the panels and the increasing useful life make them a very good source of electricity when the sun is shining. Decreasing cost of the installation, particularly rooftop, the prices have gone down because they've got the technology pretty well developed. Increasing efficiency of the panels, we talked about that. Ours are, I think John said, about 29%. They started at 1%. That's a huge, huge improvement. Use of new materials. This one is, I'm going to show you it, but we don't care because it's still undergoing testing. This is titanium oxide, and they're doing a two-level stack of solar energy production. But the titanium oxide in all the testing so far is not very durable, not likely to come online, but there's a picture of what it might look like. Increasing use of utility scale solar farms. And again, we'll talk about that in a minute, but there's problems there as well. Innovative panel designs. Now they're beginning to make panels that will be used as windows for a home or an office building, walls, and roofing materials directly, as opposed to putting panels on the roof, make your roof out of photovoltaic. Our son has a hybrid Toyota, and it has solar panels on the roof. Doesn't do much for him. Improve battery design. If we can get the battery cost down, maybe the iron air, if it really works out, would be cheaper and would be more useful for when the sun is not shining. Solar powered water treatment, they can use that for operating the panel or the station for getting our water ready for us to drink. Solar powered charging. I showed you a picture of that in Africa. And solar drones, solar powered drones for crop land survey, package delivery. And later we'll probably have an ILR talking about the drone use in IFAS and crop management. Okay, pros and cons of photovoltaic: cost advantage over fossil fuels and other renewables. materials can be recycled, no long-term storage of residue and waste. And there are no moving parts. So that's really, to me, very important because as an engineer, when you have moving parts, they break down. The NIMBY, not in my backyard. There's an article in today's paper, I threw that up there today. There's 2 townships in Michigan. One has canceled a wind farm in their township because the local people didn't want it there. And another township just canceled a large industrial scale photovoltaic energy thing. And so Michigan, along with some of the other states now, is going to, they've passed a law that the local government can do zoning, but they can't prevent installation if it proved to be useful, and the Energy Commission and the state will make the final decision on where you can put it and whether you can put it. And we went through the NIMBY here with recently with GRU wanted to put some power near Archer, and there was a great hue and cry about putting it there because it was close to a historic Black community, and they didn't want it that near their church. You need sunlight, of course, and there's storage issues, which I talked about briefly. So concentrators, suitable thermal energy storage, and retrieval from that. So you can get the energy back out, but again, that's expensive, moving parts. You have pumped hot oil going through various of the steam generator and the storage capability. But most of the items can be recycled because they're steel, iron, aluminum, no long-term storage issues. Again, it's the NIMBY. More costly than other renewable sources, more complicated engineering and solar tracking with them. You got to move the mirrors around or the concentrator around to get the sunlight where you want to collect the energy. And again, grid capacity at solar sites. I talked last week a little bit about the grid capacity and how we need a great deal of increased grid capacity. But if you're putting a wind farm in the middle of Kansas, you're not likely to be too close to a very high power line distribution system for the grid, and you have to make a connection to the grid with its own transformers. You're getting your electricity out of your solar concentrators at a couple of 100 volts perhaps, but you need to run it up to a few 100,000 volts to get on the grid. And you need sunlight. So here's your sunlight that you need. And that's it. And I'm sorry we ran over. Are there any questions?
Thank you, Walter, for this wonderful talk. What are the sun-run roofs that Elon Musk is developing? How are they different?
I'm not sure
can you
what
comment
Elon is
on that?
doing, and I don't know if Elon knows what he's doing either.
Yeah, I read about it, but I had no idea what it
Yeah,
is.
I haven't seen it, sorry.
Okay.
They're right next to you.
Yeah. What is the outlook for these small modular reactors?
The outlook for those is
About 400 megawatts.
about 400 megawatts in power, but the You're talking about the Bill Gates reactor?
I don't know anything about that, but
Well, the new scale, the ones that are modular, they were designed that way so they could get approval for the design. So they don't have to redesign each plant for each location. But they had several, 2 or 4 perhaps for Georgia. And I think they built one, maybe.
The
Big-
one in Georgia is not, it's not a new scale of care.
Uh,
They're still under the
Wait.
guise of the Department of Energy. They're supporting, there's none in existence.
Yeah. So nuclear power promises long-term availability if you can get permission and money to build it, and it has problems with waste generation and other things that I'll talk about on the 6th talk with the nuclear and
New subject. Walter, for the healthy grid or transmission system in the country, we need a proportion of base power, reliable all the time,
yes,
and a proportion of now on, now off power, wind, sun,
Right.
thermal, et cetera. Could you talk a little bit about the urgency of addressing the base power and how much we'd need?
I don't have a good figure on that, but the renewables, if they get to like 60% of occasional power, that means you're going to need at least about 80% of continually available power through coal, nuclear power, and gas-fired plants. The gas-fired plants are they're cheaper to operate, they're more efficient, but I don't know that they're building any. So we have an age deterioration problem with all of the current plants that are out there. The biomass is dependent upon being able to get some bio. And in Florida, it's pretty good because we have these hurricanes and there's a lot of trees knocked down. And if they go and collect them, they're useful. There's a waste reduction or waste production plant, which I'll talk about one of these days in St. Pete. And it's very efficient and they run all their garbage through it. The garbage truck, there's no separation. The garbage truck backs up, dumps it into a hole. Crane reaches down and pulls it over into the furnace area. And they get about, I don't remember, it's 6 or 60 million pounds of recycled metal out of what they have burned. And they have other recycled things too. But those plants, anything that's burning fossil energy, you're going to have some fly ash and some other things in the air that you need to take care of, as well as CO2.
Yeah, I wanted to ask you about hydrogen fuel cells.
Ah,
As I understand it, you can have say a wind farm or a solar farm in a remote area, and you can charge fuel cells there and transport the fuel cells to where they're used. Does that make sense, or is that?
I think you would hook them back up to the grid if you use the hydrogen fuel cells. And I saw something recently in the paper that a gallon of hydrogen takes you about twice as far as a gallon of gasoline in a fuel cell car. But the problem is generation and distribution and safety of hydrogen. Hydrogen is the smallest atom. It can leak easily through other things. So there are a lot of things to be solved by engineers in that to make it useful. But I'll talk about hydrogen later. There are some hydrogen wells that people have discovered, and they built a hydrogen well exploratory in the middle of a cornfield in Nebraska, and it came up empty. So, but there have been some.
And I guess there are also other types of fuel cells. Is that correct?
There are other types of fuel cells, and I don't know, I haven't heard anything about them recently, but 50 years ago, Westinghouse Research Lab was working with the coal industry to make a coal-powered fuel cell, and I don't think they got very far with it.
What, Bob Bernstein? It seemed missing one of the simplest uses of solar energy. It produces heat, and it's fairly easy to store heat. I mean, we had a house built in Fort Pierce in 1976, and we had a solar panel on the roof. They provided probably at least 90% of our hot water, which is a big user in a household. And you just store the heat in a big hot water tank, and
Yeah.
it's a pretty simple thing. I don't know, we had an 8 by 12 foot panel, and it's a bunch of little tubes, and it's black and it absorbs heat. Why isn't there more solar hot water use in Florida of all places?
Sure, our first heat pump in Citrus County had a heat recovery system. So as you were air conditioning the house, you were heating up this water, that moving the heat from the house into the coils, and a little pump circulated it back through the hot water heater. And all summer we had scorching hot water. And when I replaced the heat pump, they said, "Oh, we don't do that anymore. It's the new heat pumps are too efficient." And I'm thinking, wait a minute, that heat's got to go somewhere. Why don't we put it back in? So it was free. Yeah. And it was very, very hot. We had to be very careful about the shower in the summertime. You probably did too. Yeah. Yes.
Actually, to answer some of those questions, they're doing a lot of work, what do you call it, for storage, what do you call it, for example, going from the inverters, what do you call it, and then heating the salt in the salt caverns of Utah. Storage, that's another form of storage.
Yeah, I'll talk about the salt caverns later, but yeah, it is a place to store natural gas, because I had a friend who owned an old natural gas production facility near Pittsburgh, but the gas company used it as a place to put the excess gas when they didn't need it. But they're available, and the petroleum reserve goes into salt caverns. I'll talk about that later too.
And the issue with hydrogen, what do you call it, utilities are looking at burning hydrogen directly, what do you call it, as a fuel. They
Yeah.
can do it today at 30% in the existing generators. So I know in Utah, they've got a plan to ship hydrogen. They're gonna electrolyze it in Utah, ship it to Southern California, and burn it in the generators there at 30%. Mitsubishi down here is at the point where they are promising to have a generator that can burn 100% hydrogen. And I know all the utilities, I know Florida Power and Light's looking at that. And of course, they're looking at hydrogen as a storage too,
Yeah.
because they can take the hydrogen, make it one place, ship it somewhere else, and use that as a storage medium, what do you call it, to use in the generators.
And the good thing about burning hydrogen, the only thing you get out as an exhaust is water.
All right, last one. Pat Harden on Zoom, if you'd like to unmute.
Yes, I just wanted to say that we lived in a house built in the 20s in Fort Pierce, and there was a solar panel in the backyard. It was mostly what we called tar paper and copper pipe with regular window glass, and it provided on when the sun was out, enough adequate hot water for baths and the kitchen. So then the electric company came in and gave away free electric hot water heaters. So that was the end of that. So it was just a comment to say, yeah, solar power could have come a long way if it had more support.
All right, what can we look forward to next week, Walter?
Next week, we're going to talk about. Next week, we're going to be talking about wind power and wind turbines, onshore, offshore, one for your house, and those kinds of things. So next week is wind, following week is water. After that is petroleum. After that will be the nuclear power stuff.
Thank you.
Thank you for coming.